And the result I'm going to present here is the following. So Green's conjecture it was basically included in the title. So Green's conjecture is valid for any smooth curve on an arbitrary K3 surface. Everything will happen over the complex numbers. And I will certainly explain what it's all about. The main consequence of this fact is that if we have any K3 surface embedded by some complete linear system in a projective space, then the minimal resolution of the homogeneous ideal S is completely determined by the Clifford index of any smooth hyperplane section.
Do you also allow -2 curves? You allow
Yes. Actually, I'm going to cheat a little bit. That's a special case. It occupies half of the paper. I'm not going to discuss it because it needs a special.
Yeah.
So I pretend that this case doesn't exist. But so any elliptic curves -2 curves. Okay. So let me start with the statement of Green's conjecture. So I talk about Kuzuko homology. And the setup is the following. So let me remind the following definition, following Lazar's. So X is in general smooth, but it can also be just irreducible or connected. A projective variety over the complex numbers, and L in general is very ample, but it suffices to take it globally generated. On X, then we have the evaluation map of global sections. And we can take the kernel, which Lazar's denotes by ML. And we can play with this short exact sequence. Like we can take exterior powers. We can twist by powers of L. And we can take global sections. So if we perform all these operations, we will have an exact sequence like this. So 0 goes to wedge, say, P+1, ML, and H0. Tensor L, Q-1. Then a wedge P+1, H0L, tensor H0 LQ-1 to H0 wedge P ML, tensor LQ. And if I call this map delta, then the co-kernel of delta is denoted by KPQ XL, and this is called.
I can't read the subscripts. P plus Q, P+1.
This is P+1. That's P+1, and this is P.
Okay.
And this is Q-1. Okay, that's the Kuzuko homology. Of X with values in L. Okay, and there are several versions of this definition. Like, for example, we can also twist by some coherent shift everywhere here, or instead of the space of all global sections, we can just take some subspace that generates L and so on. Okay, and like any cohomology space, this Koszul cohomology behaves well in families. Notably, we have semi-continuity. In flat families with constant cohomology. Constant cohomology meaning that any cohomology spaces are have the same dimension. That's quite easy to realize. It's not very restrictive because, for example, if we consider families of curves, because of flatness, we just ask H0 to be constant. Okay. And what is the motivation for studying these spaces? So the original motivation was that Koszul cohomology computes the minimal resolution of the module direct sum of H naught LQ. So if L was normally generated, then of course this is the same as the homogeneous coordinate ring of the variety. If not, it's just the integral closure.
What do you mean by module?
Well,
it's a ring. I mean,
yeah, it's a ring, but it's a module over polynomials.
over what polynomial?
Over the symmetric power of H is over L. I should have said that. Yeah. And there are some.
But that's just the projective normalization over the.
Exactly. Yes. Yeah. Yes. And then, so that was the original algebraic motivation for introducing these spaces. Another motivation coming from geometry is that there are deep relations with geometry. And let me just quote some. So, projective normality. Can be read off Koszul cohomology, like so X in Pn embedded by L is projectively normal if and only if K not 0 Q XL equals 0 for any Q at least 2. Then we can go beyond that. So if X in Pn was projectively normal, then the ideal of X is generated by quadrics if and only if K1Q XL is 0 for any Q at least 2. and so on. So we can, instead of 1, we go further. So for K2, this would mean that the relations between the quadrics are linear and so on. Then another.
It's always going to be all q greater than or equal to 2. The 2 doesn't move up.
Pardon? The 2. Yes.
That one's just saying all the quadrics and so on are generated by those. And what's that saying?
This one?
That's saying all the cubic relations are generated by quadratic relations.
Yes, yes.
And oh, I see. So there's an L minus 1 somewhere in there. Okay.
Yeah, yeah. Okay, then we have the irregularity. Is it can be again read of Kozuka homology, where R is just H0 L minus 1 if H1 of L equals 0. So for example, the genus of any curve can be recovered from the Kozuka homology of any non-special alignment. And Castelnuovo-Mumford regularity. Can be expressed in terms of Kozuka homology. I'm not going to insist here. I'll just want to stress one particular property of Kozuka homology, which is Kozuka homology can, at least for curves, Kozuka homology can detect existence of special linear series. And this comes from a non-vanishing theorem due to Green and Lazarsfeld. It's been proven in '84, saying the following: if X is smooth and L is decomposed like L1 tensor L2, such that each of these L's have at least 2 linear sections, then K R1 plus R2 minus 1, 1X, and L is non-zero. So the existence of non-trivial decomposition like this produces non-zero Kozuka homology classes. And this is particularly relevant for curves, so especially for canonical curves. Pardon? So, particular case we're going to consider is when X is a smooth curve and L is just Kx. And if we try to apply this non-vanishing theorem to that setup, so let's see what this gives. So K will be decomposed like A, tensor Kx minus A, such that both H0 and H1 of A are at least 2. And that quantity has something to do with the so-called Clifford index. So what's the Clifford index? The Clifford index of the bundle A is the codimension of the map going from A times kx minus a to kx. That's just the addition of the divisors. And well, this quantity here of the image, sorry, co-dimension of the image. Thank you. Well, actually, this map is finite on the image, so it's just the difference. So that quantity.
Tensor product?
No, it's not tensor. It's the sum of divisors.
This is a bilinear map.
Yes. No, it's not bilinear. I mean, it's just you take a divisor and you just sum them. It's the sum of divisors.
It's not the same thing if you take the tensor method between the zeros.
No, because well, it's, these are linear systems, not vector spaces.
I don't want to work with vector spaces.
Yes, it is bilinear. That's
Of course, yeah.
But projective space multiplied by projective space maps into projective.
Yeah.
Yes.
Exactly.
Yes. I mean, of course, you can take the Z grading, heading, and so on, but then you do different things. I mean, the numbers are not the same. Okay, then that quantity R1 plus R2 minus 1 appearing in the statement will be a G. G was the genus. Minus cliff of A minus 2. So in particular, one consequence of that theorem is that K, G minus cliff A minus 2, 1, x, kx is non-zero. Okay, and now there is a small observation that's a very general fact. If some kp1 is 0, then all the others, kp prime 1, will be also 0 for any p prime at least p. So just, well, you can see this in terms of minimal resolutions, and you just write down the resolution and see that this must be true.
So look, if A is a linear system GRD,
Right.
this is D minus 2R.
Yeah, that's what it is, yes. So this is cliff of A is the degree of A minus 2 H naught A plus 2. Thank you. Okay, so we have another definition, which is the Clifford index of the curve itself. So cliff of x will be the minimum of all these allowed Clifford indices. So remember that we needed these definitions in order to apply that theorem. Okay, and but in particular we also have the same statement for the Clifford index of the curve, and so kg minus cliff x minus 2 x kx is different from 0. And now Green's conjecture predicts that this is optimal. And in view of this remark, optimality reduces to the following vanishing statement. So g minus cliff x minus 1, 1, x, kx is 0. So if this was true, for the moment it's still open. If this was true, it would give another way, cohomological way of computing, effectively computing this invariant, which is the Clifford index. And the Clifford index is lower semi-continuous and provides a stratification of the moduli space of curves. Let me just briefly say that the Clifford index has the following properties. So, first of all, it's bounded by g minus 1 over 2 integer power. That's just by perimeter theory, is the existence theorem of special linear series. And the Clifford index is also related to another invariant of the curve, which is the gonality. So, if the gonality is by definition the minimum degree of a map to the projective line. And the relation is the following. The Clifford index is lower than or equal to the gonality minus 2, that's just the definition, and it's larger than or equal to gonality minus 3. That's, again, Brill-Letter theory. It's a theorem by Coppens and Martins. Okay. And that was the, the statement. Let me, for the remaining time, just give the main ideas of proof for that result.
You mean the conjecture is true?
Well, the conjecture is true in this case.
The curves on K3s.
Curves on K3s, yes. It's a vanishing statement. So, given any curve on a K3, we should be able to prove that the corresponding Koszul cohomology vanishes. Okay, and how to do that? So we will proceed in 3 steps. So the first step is due to Weiser and consists in finding one example. So finding one example, X, in a K3 surface of genus 2k plus 1, so odd genus, and a maximal Clifford index. So in this case, kk1 should be 0, just predicted by the conjecture. And that's probably the most difficult part of the proof, so I'm going to skip it. Of course, that's an existence result. I mean, you should prove that there exists something with some properties, and finding even existence results in general is difficult. Now the second step. So here we actually leave, I mean, we can formulate everything in the K3 world.
So you mean find an example for every K3 you can produce such a curve? Or
No, find just an example of one K3 and one
K3
curve.
and one curve.
Yes,
Okay.
but for any K.
That's for any K.
For any K. But even that, it's very, very difficult. So now, I was saying that we were living in the K3 world. And now, we are going to leave this world and go to the moduli space. So that's the second step. go to mg, again for g odd to k plus 1. And this is Hirschowitz Ramanan. Actually, the order is not chronological, so Hirschowitz Ramanan proved this before Vazan. So they proved that if there was an example like this, then what I'm going to say now is true. And how to do this? So inside the moduli space, 2k plus 1, we have a divisor which Harrison Mumford denoted by bk plus 1. So nowadays it's denoted by m1 k plus 1 to k plus 1. That's just the locus of the curves C for which the gonality is k plus 1. So by Green-Letter theory, we expect that the general curve in the moduli space would be of gonality k plus 2. So that's a jump locus for the gonality. And this is a divisor. And it's an irreducible divisor. We have to compare this with the locus of curves for which Green's conjecture in this form fails. So now we have another locus. This is the locus of curves such that k1, c, kc is different from 0. And we would like to have the following. So the statement of Hirschowitz and Ramanan is that dk plus 1 and d prime k plus 1 are equal set theoretically. What would this mean? Then a curve would have kk1 0 if and only if the gonality was maximal allowed. So this is we know again that the gonality is bounded by the g plus 3 over 2, the integer part. And because of these inequalities, we would also have Green's conjecture. So one main outcome of this equality would be that Green's conjecture is valid for any curve of genus 2k plus 1 and Clifford index k. And the proof, so that's the main part of Hirschowitz-Ramanan's paper. The proof relies on a comparison of divisor classes. So we have, just by applying the non-vanishing result of Green and Lazarsfeld, we have one inclusion, namely, if we have a G1 k plus 1, then this space is different from 0. So the k plus 1 is embedded in the prime k plus 1. Then there are two more things to prove. So one thing is compute the classes of these divisors So the divisor class computation of dk plus 1 was realized already by Harris and Mumford. This is taken with the reduced structure. And the other one is computed in Kirjavitz-Ramanan's paper, and the idea is the following. So KK1 CKC will be isomorphic to K minus 1 2 CKC. That's remember that this was the co-kernel of something, a map going to H0. And if we just continue the exact sequence, we have the kernel of a map of H1s. And we apply third duality. So that's basically what it is. So this is the duality. Now, just by definition, this guy here is the co-kernel of the map of a map from wedge K H0 KC, tensor H0 KC, over wedge K plus 1 H0 KC to H0 wedge to M KC, tensor L squared. Sorry, that's K minus 1. And now, if we compute the dimensions of these spaces, H1 of this one will vanish. So we apply Riemann-Roch. We find that these spaces have the same dimension. Right? So, and we can do this in families. I mean, we can globalize this. So we can find two bundles, A and B, vector bundles on M2K plus 1, whose fibers are exactly these spaces over the corresponding point. And so we have a morphism between them. And the degeneracy locus, well, first of all, these bundles have the same rank. So the rank is equal to the dimension of these spaces. So the degeneracy locus of this morphism between these two bundles is exactly, scheme theoretically, the divisor D prime K plus 1. Okay. So we can compute actually the virtual class of this divisor. So now we get virtual divisor, which is given by the degeneracy locus. Whose class can be computed
It's
explicitly.
easier to see that the degeneration is in the expected coordinate.
Well, they have the same dimension. That's the same rank.
Because they have the same rank.
Yes, yes. It's the only case where they have the same rank.
Yeah, yes.
You can play the same game, any genus, but it's the only case where you have the same rank. Well, but of course now we have a little problem. So we have two bundles of the same rank, a morphism between them. The degeneracy locus could be either a divisor with a nice scheme structure, or the whole thing, the whole space. But this is ruled out by Bazin. So the first step says that that's a genuine divisor. Okay, so now we know the classes, and we know what are the relations between the classes. And now there is one small thing to do, which is to prove that this divisor here occurs in D prime with high multiplicity. So you just compare the multiplicities. It's like, you know, D prime, actually D prime K plus 1 is, if I'm not wrong, K minus 1. It's K or K minus 1, K. And then you prove that every time you have a curve in dk plus 1, then this space will be non-zero, but not only it will be non-zero, but it will be at least k minus 1 dimensional. So this will say something about the multiplicity. So actually this proves, together with that little missing step, which I explained in words, that we have actually equality as sets. Okay, and now we have a subset, which we need. The same holds for M2k plus 1 union delta 0. Which means we can partially compactify M2k plus 1 just by adding this border divisor, whose so delta 0. So the general member of delta 0 will be a curve with just one node, an irreducible curve with just one node. So we have a partial compactification. We can take the closure of the k plus 1 in there, and the closure of d prime k plus 1. So again, we have the k plus 1. The closure inside here is the locus of curves, such that k1, c, kc comes from 0. So exactly the same statement, but also allowing curves in delta 0. Okay, and now the final step. We are actually going to apply this equality. So now, as the first step, so we suppose that we are in the following case: x in S is a smooth curve on a K3 surface. So in the second step, we exited the K3 world. We went to the moduli space. Now we come back to the K3 world. So we have a smooth curve on S, and we take the linear system. And we prove that if C is general in the linear system, and the Clifford index of C is K, the Clifford index is known to be constant. That was a conjecture by Donaghy and Morrison, proved by Green and Lazarus in the 80s. That's constant in the linear system. And this is consistent with Green's conjecture. So if we had this, the genus was fixed to be G, then we prove, and this is what we actually prove, is that the dimension of the loci of pencils please allow me to switch from K to K minus 2, just in order not to change the indices. So the dimension of this loci, K plus n, are bounded by n for any n from 0 to G minus 2K plus 2. So this is just the locus of G1 K plus n's inside the Jacobian of any curve. Okay, and this is done by using vector bundles techniques. Because we know that the geometry of these spaces for curves on K3 surfaces is governed by ranked vector bundles on the surface. And once we've done this, this is the exception. That's why I said at the beginning that I was going to cheat, because that's actually true except with one sole exception. If L was of type 2D plus delta, where D was very ample or globally generated, and delta smooth rational curve with D times delta equals 1. So a line. So this needs special treatment, so we have to treat it separately. But with this exception, this statement holds. And now, using this intermediate fact,
I'm not sure I understand the exception.
L is of this type, 2D plus delta.
This is the monogonal case. Delta is an elliptic pencil.
No, it's not an elliptic, it's a smooth rational curve.
Yes, but it's got square. Look, D squared is positive, so the index theorem says delta squared is less than or equal to 0.
It's minus 2 precisely.
Either a minus 2 curve or an elliptic.
It's a minus 2 curve. It's minus 2.
Hmm?
It's a minus 2 curve.
What did you write? Delta D equal 1. It's delta D.
Yeah, delta D is 1. So D is very ample. Like we have a surface in a projective space, and we have another line on the surface. So the surface actually contains a line.
So the surface is nodal, and the divisor L is divisible by 2 on the nodal surface.
Yeah, exactly. Yes. Yeah. Yes. So this is a particular case because, first of all, if we look here, for n equals 0.
You're assuming that L is generated by its global sections.
Always.
Right, so you don't allow the monogonal case. You've excluded that a priori.
Yes, but 2D plus delta will be generated again by global sections.
Yes.
Yeah. And with this exception, well, because if n is 0, then we will have here minimal pencils. So this is actually stronger. It says in particular that the curve has finitely many minimal pencils.
Mm-hmm.
And this is not true here. We have infinitely many minimal pencils in this case. But again, we can solve this up. But coming back to that case, what we do, so our curve is smooth, but we can produce nodes. So we jump from, so the curve will lie in G, and we produce some nodes, and we jump to another moduli space. Actually, we jump in some boundary divisor. So what we do this, how do we do this? So we consider some general pairs of points, P0, Q0, up to Pg minus 2k plus 2, Qg minus 2k plus 2. So these are general pairs of points. And now we just glue them together. So we will get a nodal curve. The genus of this new singular curve, let me call it x is taken, so this is y. So the genus of y will be 2 times g minus k plus 1 plus 1. So it's odd. That's good news. So the genus is this one, and this property allows us to say that the monality of the new curve, so this is just done by using admissible covers. The monality of the new curve is G minus K plus, let me see, is the maximal one. So plus 3. And we can apply now this result. So in particular, so that's my new K. It's the K from here. And
sorry, which is the curve on the K3? I've got C a curve on the
C is a curve on the K3.
Right. And then
now I construct a new nodal curve just by taking.
Right. Now no longer anything to do with the K3.
No. I said that we just go in and go out from K
Right.
board.
Yes, of course.
As we wish. Yes.
But when the new G is.
The new G is 2 times. Well, we just have to add to G.
It's the old G plus. Okay.
Yeah, plus the
Oh,
number
yes.
of nodes. So should be this one.
Yes. Okay.
And we can prove just by using admissible covers that the gonality should be this one, which is maximum. That's because of this this property. I mean, if we had a pencil on the new gonal curve, this would produce some pencil on the smooth curve passing through some certain number of points. And this is not possible because the points were chosen to be general. So passing through a pair of points imposes independent
You
conditions.
mean the conjunct of the normalization of Y?
Well, the normalization is just C.
Just C.
Yeah, well, that's what I said.
Because you are group points and so on.
Yeah, I group points on C.
Okay.
And I create the new nodal
Okay.
curve. Okay, and now this result says that Y does not belong to the fact that the gonality is maximal does not belong to D, what is it? G minus K plus 2 bar. So we will have vanishing K, Y, omega Y, G minus K, sorry, there is G minus K plus 1, 1 should be 0. And now one last thing to see is that each time we create nodes, the Kozuke homology only gets bigger. So this contains K, G minus K plus 1, 1, C, KC. So this guy is 0. And this is exactly what was predicted by Green's conjecture. So I think I'll stop here. Thank you very much.